Okay, so let's just dive right in. We're about to take a trip to the most extreme places in the entire cosmos to really get our heads around how black holes don't just exist in our universe, they fundamentally warp and rewrite the very rules of reality.
You know, this quote really nails it. A black hole isn't just some super dense object floating out in space. No, it's a region, a place where the fabric of existence, of space and time is twisted into something we can barely even recognize.
So first up, we're going to explore how black holes aren't just strange cosmic quirks. They're actually the most extreme, most intense expression of the universe's own laws.
To even begin to understand a black hole, you first got to get your head around space-time. For the longest time, we thought of space and time as this fixed, rigid background. But then Einstein came along and completely blew that idea up. He showed us they're actually a single, dynamic, four-dimensional fabric that can be bent, stretched, and warped by mass and energy.
So, what happens when you take that fabric of spacetime and you don't just bend it, but you push it to its absolute breaking point?
Well, think of it like this. A planet or a star creates a little dent, a little dimple in that fabric. That's gravity. But a black hole? Whoa, that's a different beast entirely. It packs so much mass into such a tiny space that it creates a gravitational well so deep, it's not a dimple anymore, it's a bottomless puncture in the fabric itself.
And that puncture leads us to the legendary point of no return, the event horizon. Now, this isn't some physical wall you'd crash into. Instead, try to imagine space itself as a flowing river. The closer you get to the black hole, the faster that river flows. Right at the event horizon, that river of space is plunging inward faster than the speed of light. It's like a cosmic waterfall, and once you go over, there's absolutely no swimming back. Escape is impossible.
Now, this extreme curvature does some incredibly strange things to light. The black hole's gravity acts like a massive cosmic lens, bending light from stars far behind it. But it gets even weirder. There's a perfect distance called the photon sphere, where the curvature is so intense that light can actually get trapped and orbit the black hole. And yeah, you heard that right. If you could somehow hover there, light from the back of your head could loop all the way around the black hole and right into your eyes. You could literally see your own back.
Bending space is one thing, but black holes do something even more bizarre to that fourth dimension: time. That steady, reliable tick-tock of the clock that we all take for granted, well, near a black hole, that idea is completely shattered.
So let's ask the ultimate question. If you were an astronaut falling into a black hole, what would your experience of time be? And what would we, watching you from a safe distance, see? The answer is, well, it's one of the greatest paradoxes in all of physics, because it completely depends on who you ask.
And here's the part that just breaks your brain. Both of these perspectives are 100% real and valid. For you, the astronaut, your watch would tick normally. You'd cross the event horizon no problem in a finite amount of time. But for us, back on the ship, we would see your clock start to slow down, slower and slower, until you appeared to freeze right at the edge of the horizon, your image just fading away over an infinite stretch of time. Two totally different realities, happening at the same time from the very same event.
Okay, let's be brave. Let's follow our astronaut across that event horizon. Because once you're inside, the rules don't just bend anymore, they literally swap places. You're now in a version of reality that's fundamentally different from our own.
See, out here, we can all move freely in space. Left, right, up, down, but we are all stuck on a one-way trip forward through time. Inside a black hole, that flips completely. All your freedom to move through space is gone. Every single possible path, every direction you could try to go, now leads to one inevitable destination, the center. And the consequence of that switch is just profound. The singularity at the center stops being a place in space you're traveling to. Instead, it becomes a moment in time in your future. It's an appointment that you simply cannot miss.
So this inevitable journey ends at the singularity. But what is that? Well, this is the point where our current understanding of the universe, all our beautiful laws of physics, just breaks down completely.
According to our best theory of gravity, Einstein's general relativity, the singularity is a point of infinite density, where the very ideas of space and time just dissolve into nothing. The equations all return nonsense. It's basically a giant red flag from the universe telling us that our theory is incomplete and we need something new.
And this leads to a massive cosmic contradiction, a real headache for physicists called the information paradox. See, general relativity says that anything that falls into a black hole, all the information about it is just gone forever. But our other great theory, quantum mechanics, has a non-negotiable rule. Information can never, ever be truly destroyed. It's a full-on clash between the two pillars of modern physics.
But a paradox this big isn't just a problem. It's a profound clue. It's forcing scientists to dig deeper, to probe the most fundamental rules of the universe and consider some truly mind-bending possibilities.
One of the most fascinating ideas to come out of this is something called the holographic principle. It offers a wild potential solution. What if all the 3D information that falls into a black hole isn't actually lost? What if it's perfectly preserved, encoded on the two-dimensional surface of the event horizon, kind of like a cosmic hologram?
And listen, this stuff isn't just wild theories on a chalkboard anymore. We've gone from Einstein predicting all of this back in 1915 to a century later actually detecting the ripples in spacetime from merging black holes. And then in 2019, we captured the first ever direct image of a black hole shadow. We are now observing these distortions of reality with our own instruments.
So what this really means is that black holes aren't cosmic mistakes or some kind of weird aberration. They're the universe's own natural laboratories. They are designed to stress test the very fabric of existence, showing us exactly where our theories work and where they completely shatter, pushing us toward a much deeper understanding of reality.
Which leaves us with one final, profound thought to chew on. If the holographic principle is right, if all the information in a huge volume of space can really be described by the physics on its 2D boundary, well, then it forces us to ask a really startling question about our own existence. What if our entire 3D universe is just a projection from some distant 2D surface? What then is truly real?